This is the Math 30-2 Permutations and Combinations. We are on page 15 of your review notes. So let's start with fundamental counting principle, and then we'll move our way into permutations and combinations. Okay, fundamental counting principle says that if there are A ways to perform one task and B ways to perform another task, there are A times B or A multiplied by B ways of performing both tasks. So you'll commonly see questions like, how many different options are there for menus when they have 5 choices for appetizers and 4 for the salad, for example? Or you might see something like, how many different outfits can they make? And you're going to multiply together the total amount of options. Okay, then we're moving into permutations and combinations. So the biggest difference between permutations and combinations is the fact that order matters. Now I have a bunch of examples for you here of things that you might see for permutations. Anytime you're assigning positions or roles, that means that the order matters or positions are important. It might be something like a code, a password, a batting order, players in position, lining up objects, seating arrangements. You might see like license plates, things like that. Those are going to be permutations. Okay, the words arranged or arrangements is commonly going to be used. And we do have the formula on our formula sheet, and I will show you where to find it on your calculator as well. Okay, combinations. Now, the order does not matter. So what I mean by that is they are coming regardless, and the order that I select them in doesn't matter. So I am not talking about lining things up anymore. I'm just saying, hey, let's get on the bus. It doesn't matter where you're on the bus because you get to go on the trip. So examples of that are committees, pizza toppings, round robin tournaments, and handshakes. You will see the words chosen for selected used, and then of course the formula is on your formula sheet. And I will show you how to use it on your calculator. So when we start these questions, the first thing that I will talk about is how do we know what strategy to use? So let's try example number 1. Example number 1 says a dinner consists of an appetizer, an entree, and a dessert. How many meals exist? So this is an example of the fundamental counting principle. Basically, we need to have an appetizer, we need to have an entree, and we need to have a dessert in our meal. So if we take the amount of appetizers, which is 3, and we multiply it by the amount of entrees, which is 4, and we multiply it by the amount of dessert, we will get the total amount. Remember that other strategies include creating a list, right? You could list all of them out, creating a tree diagram. Those are strategies that would help you get to the answer of 36 different meals exist. Okay, so that's fundamental counting principle, and you will multiply those together. Example number 2, how many 3-digit even numbers can be formed from the numbers 2, 3, 5, 6, and 7. So this is an example of permutations. However, fundamental counting principle can be used for it. So basically, we are selecting 3 items because it is a 3-digit number. We have to deal with our restrictions first. So our restrictions in this case is that it has to be an even number. So remember, for a number to be even, the last digit has to be an even number. So the last digit can be a 2, a 6, that's it. Those are the only even numbers on my list. And what goes up top is 2 options. Just like there were 3 desserts, we have 2 options 4 numbers in that last spot. Okay, make sure you're watching for whether digits can be repeated or not. This question does not say, which means we assume that they can be repeated. So after that, I have 1, 2, 3, 4, 5 digits total for the first one and 5 options for the second number. So 5 times 5 times 2, which will give me 53-digit numbers. So always deal with your restrictions when we're dealing with these types of questions. And remember that permutations and fundamental counting principle both imply that order matters. Okay, how many ways can 8 people line up a cafeteria if Jamie, one of the 8, must be last? So here, once again, we're lining things up. That's a permutation. So anytime I see permutation, I'm going, not anytime, but sometimes I'm going to use fundamental counting principle. So since I'm lining up 8 people, I'm going to make 8 lines. 1, 2, 3, 4, 5, 6, 7, 8. And remember, the number that goes on top are the number of options that are available. So we know Jamie has to be last, which means we have one option for her. She has to be there. There's only one person there. After that, we don't have any other restrictions other than Jamie has to be last. So now, how many people do we have to go in the first spot? Well, we have everybody except for Jamie. So there's 7 options. And now it goes down by 1 every single time. So 7 times 6 times 5 times 4 times 3 times 2 times 1. Remember that if you are doing this for a written response, you need to put your multiplication symbols in there. Okay, this is equivalent to 7 factorial. Remember, 7 factorial means 7 all the way down to 1, just like is written. We can put times 1 if you want, but it's not necessary. Okay, let's see, 7. I'll just remind you where this button is on your calculator, actually. All right, on our calculator, we're going to put the 7 in first, and then we're going to go math over to probability, and then 4 for factorial. Okay, 5,040. A lot of different ways that Jamie can line up with her friends if she must be last. Okay, example number 4. How many arrangements of the letters in the word trains if the vowels are at the end? Ah, restrictions. Okay, great. So, trains has 3 6 letters in it. So let's start by making our 6 lines. Okay, so the vowels have to be at the end. The vowels in trains are A and I. Okay, so let's say the A or the I has to be right at the very end, which means we have 2 options for that one. After that, we have 1 option because I have either used the A or the I for that second last spot. Okay, so I have now done my restrictions first. I have 4 letters left to place because the A and the I have been used. So it's going to be 4 times 3 times 2 times 1. So everything but the vowels. So if we were to simplify this in factorial notation, it would be 4 factorial times 2 factorial. Okay, and that is 48. All right, so far we've been doing a lot of permutations with restrictions. Now we're going to talk about permutations with repetition. So the next question here says, how many arrangements of the word banana are there? And there's no restrictions. But I do notice in this question that we have three A's in the word banana and two N's. And what that does is decreases the amount of options, right? Because those A's and those N's, they're indistinguishable. That means that even if we switch their places, it actually doesn't change the word. So let's start with 6 factorial. Now that 6 factorial is coming from the fact that there are 6 letters in the word banana. But now we have to divide by our identical objects. So our identical in this objects in this case are 3 A's, so 3 factorial divided by 2 factorial. So if you have identical objects, and this is just one way that we could see identical objects, we have to divide by how many identical objects we have. So I'm just going to show you how to type this in on your calculator because you do have to use brackets. So 6 factorial divided by, and then a bracket has to go here. 3 times 2 factorial. And remember, 2 factorial is just 2 times 1, so you actually don't need to do a factorial there to get the answer of 60. All right, next example. Sally wants to decorate one wall in her room with movie posters. She will hang 5 of 8 posters that she owns in a single row across the wall. So I can picture it. She's got 5 laying on her bed, but she's going to hang up 1, 2, 3, 4, 5 on her wall. If Sally places her favorite movie poster in the middle, then the number of different poster arrangements possible. So I do notice that word arrangements. That means once again, we're using permutations or fundamental counting principle. We cannot use combinations. So let's deal with our restriction first. Her favorite has to go in the middle, which means we only get one option for that. After that, she has 8 posters lying on her bed. We've used her favorite, but I have 7 left over. Then I now have 6, 5, 4. So this one's going to turn into 7 times 6 times 4. 7 times 6 times 5 times 4. Okay, so that is one way to do it to give us the answer of 840. Another way or an equivalent way would be 7 pick 4. So I'll show you how to do that on your calculator. Put the 7 in first, then you're going to go math, probability, go 2 for NPR, and then put in the 4 there, and you will get the exact same answer. Okay, and remember to deal with your restrictions first. If I were to use combinations, chances are I would get an answer, but it would not be the correct answer. Or sorry, I'd get one of the answers on like the multiple choice, but it's not the correct one. All right, example number 7 says, how many different routes could be used to get from A to B if you must move only down and to the right? So you can picture it, right? Here's one path from A to B. Here's another path from A to B. Here's a third path from A to B, but I've only highlighted a few. There are lots of them. So this is another example of an identical object question. So for the identical object, the reason that they are what we call identical is because say we do follow the green path. We go down, down, then we go right, 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 right for the blocks. we can think about it as rearranging the downs and the rights. They're actually, or sorry, the D's and the R's. Those R's are all identical objects. So when we do a question like this, you want to find the total distance from A to B. So count up one path. And then you're going to divide it by the length as a factorial and multiply that by the width as the factorial. Okay, so the total distance from A to B, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, I forgot the factorial above. And then you're going to divide it by the length. The length is 7 as a factorial, and the width is 2 as a factorial. So once again, when you're typing this in on your calculator, just make sure that you're careful with your factorials, 9 factorial, and your brackets. Okay, so the answer there is there's 36 paths from A to B. All right, next example. In the 100 race at the Olympics, 8 people are competing. In how many ways can they be awarded gold, silver, and bronze? So if we think about order being important here, we're assigning roles. So it definitely matters if you win gold versus you winning bronze. So that means this is going to be a permutation question. We have 8 people and we are going to pick 3 of them to win gold, silver, and bronze. So 8, pick 3 on our calculator is 336. And remember that is equivalent to, here's my gold, my silver, my bronze. I have 8 people who could win gold. I have 7 people who could win silver, and I have 6 people who could win bronze. And gave us the same answer, so 2 equivalent ways to find it. Okay, a cast has 2 female and 3 male leads. There are 8 females and 9 males auditioning. In how many ways can the cast be chosen? So I decided to put this question in because it is tricky. It does say that we are choosing a cast for 2 female and 3 male leads. However, it does not say that we are yet assigning the roles. It just says we are choosing, and it actually says that we're chosen as well, which is a hint that we are doing combinations. So we are not yet assigning the roles, but we are just choosing the cast. So we have 8 females, and we will be choosing 2 of them. We have to use combinations. And remember that word and means multiply. So we're going to multiply that by 9 males, and we choose 3 of them. Okay, so our combination button can be found in the same spot, but now we're on to the third one. 8 choose 2 times multiplied by 9 choose 3. Okay, 2,352. Okay, so make sure you pay attention to keywords such as arranged, roles, chosen to determine whether you're using permutations or combination.